Hello and welcome to this lecture on the subject of Tribotronics, a step towards a sustainable future. We certainly have a great turnout today, so thank you all very much for coming. I am Murat Islam and I will be your host for today along with Emma Pateman, who is managing the broadcast. This lecture has been organized by the IMechE Process Industries Division Northwest Center and shared with our Lancashire area network. This presentation will discuss active tribology techniques known as tribotronics, which reduce economic losses related to maintenance in industry due to wear and subsequent failure of machinery components, such as bearings and gears, which can incorporate sensors, intelligence, and actuators to truly optimize their performance while in service, stepping beyond the conventional situation in which such components are passive devices. The lecture will also showcase some recent research at the University of Central Lancashire and Jost Institute for Tribotechnology, which help reduce energy consumption by reducing friction and increase the efficiency of machines. The lecture will be recorded and only the video will be made available later. We encourage you to contact our speaker to request the presentation slides. Please use the Ask a Question button to submit your questions and we will endeavor to direct them to our speaker at the end of the lecture. Our speaker is an internationally well-known expert in the measurement and prediction of friction, wear, lubrication film thickness in machine components. His current research focuses on the development of active machine elements, in short, tribotronics. He has led over 80 research or commercial projects and has published widely. In 2016, along with 9 other tribologists from across the world, he was selected to be presented to His Royal Highness, Duke of Edinburgh, at Buckingham Palace as part of the 50th anniversary of tribology. He is a winner of the prestigious St. Julius Grown Prize from the IMechE. And in 2018, he became the world's first professor of tribotronics at KTH Royal Institute of Technology in Stockholm. Ladies and gentlemen, please welcome our speaker for this lecture, Professor Ian Sherrington. Thank you very much.
Good morning, everyone. And first of all, I'd like to start by thanking the Northwest area of the Institution of Mechanical Engineers for this invitation to speak this morning, and also thank Murat for his very kind introduction. Today, I'm going to speak about the link between tribology, tribotronics, and how we can use these to maintain a sustainable future, and in fact address the climate crisis that we find ourselves in. This slide is a photograph from a bridge that I used to cycle across to go to work. The bridge itself has been declared unsafe recently, so I can't do that. But it depicts the River Ribble, and you can see that there are several meters between this fairly typical level of the river and the top of the banks. Between about 1940 and 2010, the river flooded the grass plains on either side of these banks twice. Since 2010 to now, it's also done it twice, and nearly flooded on several other occasions as well. So the frequency of flooding is increasing. Climate change is evident to people who are probably 20 or 30 years or older by personal experience. And what I'd like to do is to draw your attention to this quote by an Arctic explorer, British Arctic explorer Robert Swan. He says, "The greatest threat to our planet is the belief that someone else will save it." We often look to politicians to help guide us in plans to control climate change. But in fact, we should start to imagine that controlling climate change is everyone's responsibility. And I'd like to encourage all engineers and all tribologists to think along these lines. And part of my presentation today will be addressed towards this particular challenge. So the presentation will address some issues connected with climate change, good practice in tribology, and the future of tribology and tribotronics. Okay, so back in the late 1800s, Svante Arrhenius, who was a Swedish scientist working in Uppsala, found a way to measure the amount of carbon dioxide in the atmosphere. And he suggested that this carbon dioxide may be responsible for controlling changes in the atmosphere. He also suggested that the amount of carbon dioxide was increasing. He was the first person to notice that, although it wasn't clear why it was increasing. He found that it was increasing. Back in those days, climate warming was considered to be a good thing because scientists in those times thought that would allow greater production of food. As we worked through the 1900s, it became more and more clear that climate change was due to human activity. And in the 1960s, David Keeling was the first person really to get a good grasp of the fact that human activity was definitely causing global warming. It still wasn't certain in a statistical sense, but the concern was so great that this organization was formed, the IPCC. The IPCC was established in the late 1980s by the United Nations and the World Meteorological Organization. And its objective was to provide a clear scientific view on the current state of knowledge in climate change, as well as observe its impacts. The IPCC itself does not do any scientific research. It collects together scientific, technical, and other information from other authors and tries to produce an average of that information. And it produces occasional reports. So far, 5 assessment reports have been produced to advise government policy around the world. The next report will appear in 2022. Some conclusions from the last report are quite disturbing. It's established that 95% to a 95% confidence limit that human activity is the dominant cause of global warming since 1950. Obviously, the increase in carbon dioxide in the atmosphere is causing this, and if we look at the changes in these so-called greenhouse gases over the last 800,000 years, levels at their highest over that period of time. And much of that increase has taken place during the last 100 years or so. One of the things I'd like to recommend you to do is to watch a program called A Life on Our Planet by David Attenborough, which he describes as a witness statement. And the program works chronologically through the life of David Attenborough, recording the level of carbon dioxide in the atmosphere and the population of the world, demonstrating how within a lifetime visible changes have taken place on not just a small scale but a quite dramatic scale. It's a really moving documentary. As the world warms, the energy needs to go somewhere, and the sea, the oceans, provide the biggest heat sink for this energy. So much of the heat that is accumulated on the planet finds its way into the sea is warmed. Also, much of the excess carbon dioxide that's generated finds its way into the sea as well and changes the acidity level of the sea. So not only is the sea becoming warmer, but also the acidity of the sea is increasing. And this has several effects. So we see the loss of coral reefs. We see also the reduction in the size of the Arctic and Antarctic ice sheets, which in fact melt from underneath due to the warming sea. And very large pieces of land are often released, frozen sea are often released. Most recently in 2017, a large part of the Antarctic was so-called carved off and that was labelled A68A. This piece of the Antarctic is huge. It's larger than the size, larger than the area of Greater London. It's still around, and it's moving around just close to South Georgia, not melted yet. The IPCC, through their monitoring work, produce a range of predictive models which are illustrated by the graph on the right-hand side of this slide. And unfortunately, there's no pointer in this system, so I'll have to try and describe what you see here. On the x-axis, we see the amount of anthropogenic carbon dioxide, and on the y-axis, we see the Earth's temperature increasing. There are several coloured lines on here. Most of the coloured lines are IPCC models of what might happen in the future. The black line is where we are measurements of where the planet is at. And the most recent measurement, as you can see, is 2010. We're tracking the worst case scenario, which isn't good. And we need to try and find ways of reducing this rate of increase, if not reversing it. Let's move to some tribology. Across the planet every year, we generate something like 500 million terajoules of energy. Around about a quarter of that is used to overcome friction. So data has been collected by Kenneth Holmberg and Ali Erdemir, and this is published, as you can see, in the journal right at the bottom of the slide. And they've tried to characterize these losses to identify where these friction losses take place. So the greatest losses, you can see, are related to the transport sector, where around about 30% of fuel energy is lost in friction. 20% of energy in industrial and manufacturing applications is lost in friction, and unsurprisingly, it's a rather lower amount in residential type applications. Globally, we can see that somewhere between 15 and 25% of the energy that we generate for use across the planet is used to overcome friction. That's about 100 million terajoules a year. That's a pretty difficult figure to try and get your head around. So I've tried to illustrate that by looking at it in terms of the kinetic energy that we see in a typical tornado. A typical tornado has a kinetic energy of around about 62 gigajoules. And this 100 million terajoules that's lost in friction is therefore equivalent to approximately 1.6 times 10 to the 9 tornadoes, 1,600 million average tornadoes. From the news, most of us are familiar with the amount of damage that amount of energy can cause when it's released into an urban environment. And I think this huge figure gives us some kind of feel for the amount of energy that we are really wasting in overcoming friction. The consumption of raw materials is mainly connected with wear. So we're talking about adhesive wear and abrasive wear processes. Of course, we consume materials for other reasons, through fatigue and so forth. However, a large proportion of the materials that we waste are basically products which have worn away by a range of tribological processes. When we think about solids, we consume, as a planet, around about 100 billion tons of materials per year. That involves around about 50 billion tons of minerals and 10 billion tons of ores and so forth. Only a very small proportion of this is recycled. So we see 70 billion tons of waste and 2.8 billion tons being recycled. Still a huge amount, but nothing approaching 100 billion tons that we actually consume. We see a similar picture in in the context of liquids. Across the planet, we consume a huge range of different types of liquids. Obviously, one of the ones that's relevant to tribology is lubricants. And across globally, we would use about 4,500 million tons of crude oil, and much of that will be lost into the atmosphere or lost into the ground rather than reprocessed. You can see this very small figure of 3 million tons being reprocessed in the EU in 2026. So what can we do about that? Well, back in 1966, Lord Bowden invited an industrialist called Peter Jost to try and identify what was causing the very large amount of money lost in maintenance costs. So the UK was still recovering from the Second World War, and we'd seen the very rapid installation of machinery for conventional manufacturing, moving away from the defence industry. That had been done very quickly and very suboptimally. So by 1966, a large amount of money was being used to try and maintain this equipment. Peter Jost and his panel, which you see here in a room in the Institution of Mechanical Engineers on the right, were invited to try and understand why this was happening and to offer proposals to the government to put this right. They produced a report which is commonly known as the Jost Report, and you can see the copy from the University of Central Lancashire there on the right of the slide, quite well used. And within this report there were a wide range of recommendations, including things like establishing a network, in fact, of national centres of tribology, recommendation to teach the good practice in tribology in universities and so forth. One of the interesting factors was that the economic savings were very significant, in the hundreds of millions of pounds even in the 1960s. And only a small proportion of these savings were related to reducing energy use. Energy was cheap in the 1960s compared to where we are now, and this was a very small component of their thinking. However, by the 1980s, there'd been a war in the Middle East, and we were no longer able to move ships through the Suez Canal laden with oil. They had to go around the southern coast of Africa, and of course it cost a lot more. That situation led to the development of supertankers, but in the interim, fuel was very expensive, and in fact the price of fuel went up by a factor of about 4 over a period of a couple of years. So imagine what would the situation now. Fuel now costs something like 120, 125 a litre. So in 2 years that might go up to £5. It had a very dramatic effect on the way that society behaved and operated. And so at that point, tribology's impact and being able to control energy loss started to become important. As we progressed through the 1980s and the 1990s, it became widely recognized that tribology was a tool that we could use to support sustainable engineering. And so we began to see tribology not only as a tool to reduce economic costs, but as a tool to reduce the consumption of materials and the consumption of energy. So one of the things that the Jost Report recommended was good practice in tribology. Tribology is focused on operating devices more efficiently to reduce friction during operation, and also minimizing wear to reduce the use of materials, and also to reduce energy use during production processes as a secondary effect. And we can see that in that situation then we reduce the collection and pre-processing and transport of raw materials, we reduce manufacturing carbon footprint, we reduce the amount of transport required of finished products, and so on. So it starts to be a very positive feedback loop which is generated by using fewer materials and reducing wear. And as you can see, it covers a whole range of applications, from simple tribological components like nuts and bolts, threaded fasteners, right through to spacecraft. However, as time has gone by, the impact of tribological development has begun to increase. One of the important trends that we see in engineering is that people expect to be able to operate at bigger loads, higher energy densities, higher speeds, lower weight, reduced cost, and increasingly with a lower environmental impact. And tribology, for decades now, since the 1960s, has facilitated this by a range of interesting and different trends. So one of the trends, for example, is the use of lower viscosity lubricants. And if we use lower viscosity lubricants, we can reduce viscous drag and reduce energy loss in hydrodynamic contacts, for example. One consequence of that is that the lubricating films in these contacts get thinner and thinner, and I'll come back to that in a moment. We also see the development of environmentally friendly lubricants, probably better described as environmentally adapted lubricants. They are less damaging to the environment, but in many instances their performance is also not as good, so they decompose more easily and they have poor compatibility with other materials such as rubber seals, for instance. So that's an issue. We see the increased use of hard coatings to generate wear resistance, often deposited by processes such as physical vapor deposition or chemical vapor deposition, both of which have very low wastage rates. So that's quite good in terms of minimizing manufacturing disposal requirements. In parallel with this, we also see legal constraints increasing, so reduced use of environmental damaging elements such as chrome, lead, and tin, and so on. So we are obliged to try and find alternative replacements for many of the soft coatings that we use in tribology for sacrificial surfaces, for misalignment and so forth. On this side, we see two graphs. The slide on the left illustrates the mass of a specific rolling element bearing, or in fact a range of rolling element bearings that have been produced by SKF, which have roughly the same performance across the decades. So you can see in 1950, the mass of this bearing with a particular performance will be 1.8 kilograms, 18 kilograms, and that's come down now to just over 4 kilograms. The key point about this graph is that the curve is getting shallower. The slope of this curve is getting shallower. So future possible improvements in mass reduction are getting less and less possible. If we look at the curve on the right, this curve illustrates typical operating film thicknesses since 1900. And you can see here that in 1900, operating film thicknesses were of the order of 50 micrometers, typically in journal bearings, for example. And that has decreased as the decades have gone by. And I've taken some data from a paper by Duncan Dowson here called the thinning film. And you can see now that as we move through the decades since 2000, then films can be extremely thin. So certainly a few nanometers in some applications through a process of asperity lubrication. In many hydrodynamic applications, these films are also less as well. So instead of it being 50 micrometers in hydrodynamic bearings, we can certainly get down to 5 micrometers, benefiting from improvements in engineering tolerances and manufacturing tolerances across the decades. Another trend that we see is the increasing use of condition monitoring. One of the benefits of condition monitoring is that it allows us to operate not just components, but entire systems in a state that we can know is safe and reliable until such point that they might need servicing, rather than servicing against a specific interval or replacing a fluid, such as a lubricant or a component, at a specific time interval. So we've moved away from a maintenance process in which we replace parts and lubricants on the basis of time to processes where we replace parts on the basis of their condition, and we can measure their condition by a range of sensors, so we have condition-based maintenance. That helps us as well move on to a second stage where we can try to predict the remaining useful life of these components through processes related to predictive maintenance. So we can collect data from these sensors about vibration, about operating temperature, about perhaps acoustic emission, fuse that data using various data fusion techniques related to machine learning in order to try and make increasingly reliable predictions about the performance of these devices. So high-value assets, such as large engines on ships, aircraft engines, wind turbines, and so forth, are being increasingly monitored. And we would apply these kinds of techniques where an asset would be a critical asset in a large system, where there's perhaps a significant safety risk, where we need to plan the downtime of a machine for maintenance, and perhaps where we've got a new kind of device, a critical asset, and its performance isn't known. Anywhere where fault propagation might lead to a high cost. And we've got this wide range of different kinds of measurement methods as well to apply, so vibration analysis and acoustic analysis and thermal analysis and so on. And we operate this kind of scenario within a loop like this. So the tribological element is monitored by the sensor. The sensor allows data to be observed by a maintenance engineer. The maintenance engineer at an appropriate time then would go and apply either perhaps a replacement part or some kind of maintenance activity on the tribological element. And the increasing use of sensors means we can do this in a more and more efficient way. However, what I'd like to propose is that we move to a more complex system in which the tribological element is monitored by the sensor, and the sensor sends its output to a control unit which can automatically operate an actuator to modify the operation of the tribological element. And you can see it associated with this. There can be a user interface, so this tribological element can be monitored, and we can also send information to machine learning systems, which might be web-based or might be part of embedded intelligence in the machine, so that machine elements can operate with much more optimal in much more optimal conditions. This might seem far-fetched. However, I'd like to draw your attention to the fact that things like automatic braking systems have become very commonplace over the last couple of decades. Most cars have automatic braking systems now to control wheel skidding. So if each of the wheels on a car has its rotational speed monitored, if we apply the brakes and 3 of the wheels are rotating but 1 of them isn't, then the automatic braking system can do something, perhaps release the braking pressure on that wheel, that specific wheel, to allow it to rotate and allow the driver to retain control of the car. This is a Tribotronic system, and it's very common, it's very widely applied. Also in automotive applications, we've got things like automatic gear changes, automatic transmissions. And within these transmissions, we have actuators which can control the contact pressures on the transmission elements as gear changes take place. Again, entirely automatically through a feedback loop like this, completely without the knowledge of the person driving the car. In addition to this, we see lots of other trends taking place in engineering as well, which we can take advantage of in order to build our tribological elements. So we have low cost, embedded intelligence, sensors, we have communications technology such as Bluetooth, we've got internet connection of machines through the Internet of Things, and we've got smart materials and smart coatings that allow us to do increasingly helpful things in terms of being able to have self-repairing parts which communicate their condition perhaps through thermochromic dyes and so forth. We also have the development, very rapid development of additive manufacture, which we can use to manufacture parts which would hitherto be either very expensive or impossible to manufacture through conventional techniques. And we can build these parts that have functional properties as a consequence of their geometry. We can integrate sensors, we can make them so that they are more recyclable, and indeed we can build these parts out of recycled materials. And we can also incorporate functional materials within the structure of these different kinds of parts. So if we think about the evolution of a bearing and how it might look in the future, on the left-hand side, perhaps 3 centuries ago, a journal bearing was a straightforward circular cavity into which a rotating shaft might sit, perhaps either dry or with some kind of basic grease-type lubricant. And as we've moved through the centuries and through the Industrial Revolution, this arrangement has become increasingly sophisticated. The spacing between the shaft and the bearing has been more accurately tailored to the function of the device. We've begun to understand in the 1800s how we can predict things like the load carrying capacity of the bearing, where to put the grooves, where to put the oil supply hole, and so forth. And as we've moved through the 20th century, we've gained control of the materials of this component. So the microstructure of the coatings and the microstructure of the material of the bearing have improved and allowed the performance of this device to get better. And where we are at the present time now, we have these quite sophisticated components, even though they might look outwardly simple. We're beginning to use asset management through condition monitoring and predictive performance. What I think we'll add in the future are these controllable elements with this feedback loop that allow us to directly change the properties of these devices, changing their shape, changing the viscosity of the lubricant, changing the flow rate of the lubricant, and many other properties of these devices to both keep them operating longer and to make them functionally more effective. Tribotronics, a feedback loop involving sensors and actuators. At the University of Central Lancashire, we've been developing different kinds of tribotronic components now for some years, and I'd like to show you a few examples. This first example here is a lip seal. You can see on the top left then the structure of a lip seal. At the bottom, unfortunately I can't point to these slides, apparently there's no pointer in the system, but at the bottom of the lip you can see the shaft, and that lip is pressured against the shaft using a spring that's built into the device and the natural compliance of the seal itself. The graphs to the left are effectively derived from simple capillary models of the contact, but the purpose is to try and illustrate how this device behaves. So on the top graph you can see that as the film thickness between the shaft and the lip seal increases, the flow rate, or leakage if you like, of this device also increases. On the bottom slide you can see that as the film thickness increases, then the power loss also goes down. Now these are of course very simple analytical models. However, it it illustrates that there is a significant compromise to be had. If we want to prevent large leakage, then we need a small film thickness. But if we have a small film thickness, then we have a high power loss. And we need to find some kind of balance, some kind of compromise between those two parameters. If we have a controllable system, a system that able to control the pressure of the seal against the shaft, we can modify this compromise in any way that we like at any point in time. So if we can adjust the actuator under circumstances where we want very low flow rates but are prepared to tolerate high power loss for a short while, we can increase the contact pressure. And when the converse is true, if we don't mind the large flow rate but we would really want to reduce the power loss, then we can reduce the contact pressure to allow the film thickness to increase as we operate this device. We've built a seal which we're able to change the contact pressure in using a very neat little actuator. And this is our test rig. You can see that there's a shaft in the center of the test rig, and the outside of the test rig is transparent, and that allows us to use thermal camera to produce the image on the right, so we can measure the contact temperature between the shaft and the mechanical seal, the lip seal. And we can measure lots of other things as well, so we can measure the power loss. We can also move this component laterally, so we can simulate out of line effects and how effective it is to apply the actuator to compensate for misalignment between the shaft center and the seal center. The graph up on the upper right illustrates the effect of on the x-axis illustrates the effect of radial pressure and leakage. So you can see that when the radial pressure is light, the leakage is high. When the radial pressure is high, the leakage is low. Very much following the graph shape on the previous slide. Although they've been turned around, but effectively you can read for film thickness here contact pressure. So when the contact pressure is high, the leakage is low, and when the contact pressure is low, the leakage is higher. Another project that we've got is to develop a feedback control system for a large two-stroke marine engine. These engines operate with an isolated cylinder because they use very low quality fuels. There's a lot of sulfur in the fuel, and that generates sulfuric acid during combustion processes, and the arrangement prevents these sulfuric compounds reaching other parts of the engine and causing corrosion. As a consequence, lubricant is supplied to the top of the cylinder by a spray, and this lubricant conventionally will contain an alkaline additive to counteract the production of the sulfuric acid. So as the engine might increase speed or need to increase power, a larger amount of lubricant is injected into the engine in order to make sure that an appropriate quantity of additive is supplied to compensate, to reduce the corrosion. However, that means that far too much lubricant is injected into the engine. So if we think about a fleet of 30 ships or so, 30 ships might use something of the order of 3,000 tons of lubricant a year. If we could save just 5% of that, well, we'd probably save 500 tons of lubricant, cylinder lubricant. And this being a more or less complete loss system, it also means that we would save something like of the order of 1,500 tons of carbon dioxide from being ejected from the engine as well on an annual basis. So we've devised this system, we've separated out the control of the lubricant additive and the control of the lubricant. So each of these substances can be injected into the engine separately. We can control the amount of lubricant injected into the system by measuring the hydrodynamic film thickness using a film thickness sensor. That feeds a signal to our control system, and we can increase or reduce the amount of lubricant that's injected into the engine to control the film thickness. And then separately, we can control the amount of additive that's injected into the engine to compensate for the increased amount of acid in the fuels. So it's quite a long-term project, and one of the advantages of building a system like this is that it's allowed us to do some very interesting research to observe how lubricant moves around an engine. So this slide shows us on the bottom left what happens as we start the engine, or start the test rig, as it's not a firing engine, start the test rig with no lubricant in, and inject lubricant in at different rates, and you can see that the build-up of the hydrodynamic film happens at different rates if we inject it at different rates, but they all stabilize out at roughly the same value. So lower rates you can see, for example, the blue line, and higher rates, for example, you can see the red line. The graphs on the right are more complex. These graphs represent the degree of filling of a piston ring as a function of time. And there are graphs for each of the sensors that we've put into our cylinder. So the graphs at the top represent the sensors towards the top of the cylinder where the lubricant is injected, and the graphs at the bottom represent the sensors at the bottom. The shaded part of the graph is the degree of filling between the top and the bottom of the piston ring as it goes up and down. So you can see the top two are filled fairly quickly, time starting at 0 at the bottom on the y-axis. But the lower down that the sensors are placed in the cylinder, the longer it takes the lubricant to arrive there and start to do its job. Now, this might be quite obvious that it takes time for the lubricant to arrive there, but until this test equipment was built, nobody really had any idea of how many strokes or what period of time this process took. Some of the advantages that we can think about might be derived from a system like this if it was fitted on a ship. First of all, that it does separate the lubrication system from corrosion control system. And the value of that is that it does permit very large quantities of lubricant, in principle, to be saved by this device. Of course, there's a double benefit. We get lower emissions, as I've explained. So we see lower amounts of carbon dioxide going into the atmosphere. The operator sees a benefit from a lower operating cost. We should have better corrosion control as well, because it's not good to supply too much or too little of the additive to counteract corrosion. And it's automatic. I'll come back to that in a little while. And it's also bespoke to each system. So each ring and each cylinder can moderate itself independently in order to control these parameters. Finally, this is a project that we've just started recently. Tribotronic control of tilted pads. Tilted pads are used in a wide range of applications. They may be quite small on the scale of millimeters, or they might be quite large, as in this example. If you take one of these pads, it's probably about the width of a couple of adult hands. And these pads are used in applications like hydropower stations or submarine propellers, that kind of thing. And controlling them should offer some useful opportunities. So we should be able to minimize power loss, for example. We should be able to manage their vibrational characteristics, certainly move around from their resonance points. We should be able to compensate for misalignment and regulate temperature to reduce the degradation rate and have longer lives of lubricants. Many of us will be used to analysing the performance of tilting pad bearings using these non-dimensional coefficients. And the graph up here on the right is useful because it allows us to understand that, again, just like the ellipse here, we can find optimal points on these curves. So if we take, for example, the solid line, which is the outlet temperature, represents the change in outlet temperature as a function of the inlet-outlet film thickness of the bearing. So if we change the tilt, we can change the performance of these bearings. And the other curves represent other parameters such as the load carrying capacity and the required flow rate to keep the bearing operating. And you can see that as you move backwards and forwards along the x-axis, then the ratios of these lines change. So we can, for example, change the outlet temperature without too much penalty in load carrying capacity by changing the inlet to outlet film thickness ratio, perhaps with an actuator. As academics, at least, we're very used to creating models to try and understand, try and predict what might happen in engineering systems. Tribologists do this all the time. It's very helpful to be able to do that. And what we aim to do is to try and get a match between our experimental data and our model. It's not essential that we understand a system in order to be able to control it. So if you think about your house, for example, you've got a central heating system and it's a feedback loop, yes, but you don't need to have a model of the thermal heat loss of your house in order to heat it effectively. What you do is allow the automatic control system to adapt to the conditions of each individual house. And the same is true in Tribotronics. We can use these control systems to control these devices without a thorough understanding of the principles of operation of that component. However, as academics, often we try and build these models, and certainly that's what we're trying to do in the case of the examples that I've shown you today. So fundamental models are useful for these devices, but they're not an essential prerequisite to being able to build a tribotronic device. Coming to the end of the presentation now, and what I'd like to suggest to you is that tribotronics is the next step of development of tribology, which gets us over this issue where we are reaching the end of the line, the end of the curve in our development possibilities in design. The curve is flattening out. It might be that early tribological devices are not particularly elegant, not particularly convenient solutions, but as we implement more and more of them, they will become elegant, rather like the automatic braking systems in cars, for example. They offer a lot. They offer machine information, user information about the machine to the user. They offer a managed life, which should give us greater reliability and a longer life. They offer us more functionality, so we can control different aspects of their operation at different times. They offer increased autonomy. We can actuate their capability and performance automatically to suit our needs, as I've explained. And there is the possibility of communicated learning as well. So if we think, for example, about a field of wind turbines, if there is an abrupt, potentially damaging gust reaching the first wind turbine in the field, gets sensed by one of the bearings in that system, it can send a message to all the other wind turbines in the field, warning that that damaging gust might be coming along, and allow those machines to accommodate a different operating condition that can compensate and protect against that potentially damaging gust. It also offers the opportunity to control maintenance schedules through the data and the prediction of remaining useful life. And of course, in today's world, many people speak of Industry 4, but these intelligent components, these intelligent machines can be integrated into the Industry 4 framework. They are perfectly suited to that kind of application in these machines: data collection, big data, and connectivity. Crucially, if I take you back to my original slide, they offer lowered operating impact, lower friction, lower wear, fewer emissions, less waste. So, to conclude, tribology since the 1960s certainly has contributed significantly to improving the economic and environmental health of our planet. But we're seeing now, with the development of engineering and electronics and communication, that we can automate these systems in the form of tribotronics for a wide range of different kinds of machines. And possibly we might find ourselves not only adapting the components that we've used traditionally, but perhaps we'll see new types of devices being designed, particularly manufactured through additive manufacturing, new components that we would perhaps never have thought of before for integrated solutions. And there's a wide spectrum of applications that can benefit from these new kinds of proposals, new kinds of components. I would just like to finish by drawing your attention once again to the fact that the greatest threat to our planet is the belief that someone else will save it. And I'd implore everyone who's attended this seminar to think about this in their professional life and try and think about what they can do to perhaps assist in saving our planet. Thank you very much.
Hi, Ian. Thank you very much for your great presentation here. I suppose it's a good time to open it up for the questions, if that's okay with you. I have got quite a few good questions here, actually. If that's okay, I'll ask them one by one to you, and hopefully we will try to answer them as best as we can, really. So the first question I've got here is, do your friction loss numbers relate to losses in, do they relate to the mechanical system losses, or do they also account for the general frictional losses, like the aerodynamic losses or hydrodynamic losses as well in the system?
Yeah, that data was taken from the paper by Kenneth Holmberg and Ali Erdemir, and I'd like to suggest that the questioner has a look at that. I'd be happy to, in fact, I can probably go back to the slide and show the reference.
If that's, I think slide 9, if I may change the slide for you.
Have a go.
Okay. Just bear with me a second here. I think I'll just jump to the slide.
Okay. The exact methodology is in this slide, and I'd recommend the person to have a look at this.
Friction and wear costs around 8% GPM.
That's 0.15. That should be 2015. Now there's a 2 missing from the reference.
Okay. Thank you very much. I will go to the second question, which is a bit of a longer question. I will try to summarize it, if I may. Regarding the practicalities of using actuators on tribological elements. Let's say if you have a machine with several bearings on a turbo expander generator set with a gearbox, all the bearings on the turbo gearbox and motor share the same lube oil system, obviously, probably in most applications anyway. If one bearing is starting to get hot on the gearbox high-speed shaft, how would an actuator assembly then respond to increase the life of that component?
Yeah, I think development of the actuators is probably the biggest challenge in the subject. And certainly when we are doing our research, it takes us some time to trial different approaches to different kinds of actuators. But in this situation, I would envisage that every bearing has its own set of actuators and its own control system and can operate independently. So probably, an intuitive solution will be to use an actuator to increase the film thickness on that one bearing, so that it can compensate on its own account. Yeah.
Okay, so multiple control systems for probably every single bearing in the system that are crucial to the failure mechanism, maybe.
Absolutely, correct.
Okay. Another question here: how does the lip seal with variable contact distance work? Are you replacing the garter spring with a pressure tube band so that you can increase and decrease the air pressure to modulate the missing spring forces?
We've tried we've tried a range of different kinds of actuators. We've tried materials that we can, actual material that we can change the contact pressure with. We have tried the method that is suggested by the question, but we have a mechanical actuator in this system.
So, okay, there's no hydraulic involved, it's proper mechanical pressure.
No, it's mechanical.
Okay. Another question: if I have large machines designed in the 1990s, is it time that I started looking into new bearing types from the OEMs? Would there be any great gains from from technology less than 30 years old? What reduction in friction losses have been made in the last 20 years?
Yeah, that's a very specific question. Certainly, bearing performance, bearing lifetime of rolling element bearings has improved across decades. So that's certainly the case. The general improvement for other types of bearings would generally be in the tolerances, so in the film thickness that they're able to operate with. It's a difficult question to answer because there are certainly hydrodynamic bearings in power stations, for example, that have been there for decades and which work perfectly well because they're hydrodynamic and properly designed. They don't necessarily wear so much. Perhaps any damage that might result will be cavitation damage. I guess it depends on how good the bearings that were installed in the first place were, whether they were top of the range or bottom of the range. But power loss is dependent on film thickness for a hydrodynamic bearing, so it depends what film thickness they're operating at.
Yeah, I mean, if you just look at the graph here on the left-hand side, based on how they reduced the mass of a bearing over the years, you can see from 1990 to 2000, there is significant mass reduction actually compared to sizes in relative speaking. So if you are in 2010, 2020, I assume the trend will follow. So it tells you your bearing mass will at least reduce if you go down that route. And I'm sure
if it's a rolling element bearing, then I think the gains are getting smaller. Let's put it like that. That's what that graph is intended to illustrate. So the gains are getting smaller. But it depends. I mean, these kinds of bearings fail by a fairly kind of statistical process. So the lifetime of the bearings in whatever application it is will be quite clear statistical pattern. And if that fails, there's always an argument about if a device is old but still operating, should it be replaced to operate more efficiently? But the problem is that obviously you use a lot of material to replace it, a lot of time, a lot of energy to replace it. So from an environmental perspective, it might not be worth replacing. But from a day-to-day operating cost perspective, it might be. It's not an easy question to answer. It's like, is it better to repair an old car or throw it away and get a new one? Trade it in and get a new one. From an environmental perspective, it might be better to retain the car. It's tricky.
And I suppose commercially, how much of a saving is enough for you to make as well, isn't it?
From an economic perspective, it's a different question.
Yeah, sure. Okay, the next question I've got here is, would the tribotronic lubrication system also reduce particulates generated in the exhaust gas?
I think it probably would. It depends on what else is in the system. Um, soot particles in combustion processes are obviously problematic. A large proportion of the emissions that come from ships in particular come from the fuel. And so the proportion of emissions that come from the oil or the lubricant are less. But it certainly would reduce the particulates, but the question is by how much, and I've no experience to be able to answer that question.
Of course, okay. Another question here, how does your Tribotronics proposal for low-speed 2T cylinder lubrication differ from the existing commercial OEM offers, such as Alpha lubrication system from MAN, maybe?
These systems that are used currently are spray systems, and typically the way that the spray systems are operated is that they start the engine, a new engine would be running with the spray system implemented, and they would turn down the feed rate as they test the engine over a period of days and sample the lubricant from the stuffing box to look for debris particles from the engine. And when an appropriate level of debris particles is agreed upon, then that's the feed rate for that engine. It's tricky because this feed rate depends on the operating conditions of the ship. So it's been found, for example, that sea state can change the operating film thickness in the engine. And so this isn't really a complete feedback loop system. It's a system that looks at the load on the engine, looks at the speed of the engine, and determines a feed rate based on those two parameters. So it's not responding to the lubrication requirements of the engine. It's actually responding to the corrosion resistance requirements of the engine, which is really the point I was trying to make. If you separate the corrosion requirements from the lubrication requirements, you can feed in very often a much lower proportion of lubricants into the system to keep it properly lubricated, and separately determine the additive supply quantity in order to compensate for the acidic content from the combustion process.
Okay. Thank you very much for this. I've got a few more questions. I think I will extend the time if needs be a little bit, if that's okay with the people. Is there a way to implement AI for detection on corrosion on systems so that we can use anti-corrosion material on the system?
I guess there is. I've never done it, but it seems that you can apply AI for almost anything these days, and it depends on the context as well. So if it's a complicated system, then it's probably much more valuable to be able to do some experiments and collect some data that you can then apply into a machine learning system to understand if a particular proportion of contaminants is present, what the likelihood of corrosion will be, and what to do about that at any particular time. Machine learning is an exciting range of possibilities for the future, and certainly it's being implemented quite widely in a way that probably most people don't understand within industry, to try and predict the performance of all kinds of different sorts of machines.
Yeah, sure. I've got a question here, potentially from one of your students, actually. Is there any scholarship on research for UCLan master students or any PhD scheme available?
Okay. From time to time, we do have scholarships, and we've recently appointed a couple of PhD students to work on these topics. One on the bearing system that I illustrated here, and another to work on a system to develop an electronic nose to monitor lubricant degradation and try to understand what the degradation components are in under thermal stress and under mechanical stress. At the present, we don't have any adverts for PhD students, but if people can be sponsored by companies or perhaps their governments, if they're overseas students, then we're always able to consider applications into the team.
Okay.
But there are no scholarships at the present time.
So another way of getting that scholarship is find a company that will be willing to pay for your tuition fees and everything.
Sure. Some of our PhD students in the past have been part-time students working within companies who have problems that are related to the kind of research that we do, and we're very happy to have them with us one day a week and develop a relationship with the company and address problems as they see them in the context of their own business. So there's plenty of opportunity to do that, and indeed we'd be very excited to do that because we have something called the Engineering Innovation Centre, and one of our objectives is to try and link to industry in the north and try and serve industry in the north by using our research to help them solve their problems. So I'd be very pleased to speak to people from companies.
Excellent. Yeah, thank you. Okay. Shall I ask this? Are there any sensors are existing or newly developed based on the presentation you give? Is there any completely new sensors or things you are developing right now?
Well, one of our long-lasting developments, if your long-term developments, is to develop and build oil film thickness sensors, particularly for hydrodynamic applications. And the evolution of those sensors has been going on now a very long time. You'll see that we use them a lot in our research. And as I've just mentioned, this gas degradation, the E-nose, the electronic nose, to detect the degradation of lubricants by looking at the degradation products, is a system that we've begun to work on comparatively recently in earnest. So we built one of these systems in the past and found it very effective in observing changes in the state of lubricants. Actually, in a Formula Ford car, our motorsport guys run in Formula Ford competition, so we monitored the headspace of the lubricant in a Formula Ford competition car over a couple of 100 miles, and we could very easily identify changes in the lubricant composition.
Right. So what about the sensors you used in your test? And have you had to develop them, or were they just standard items?
Often we build sensors for all kinds of applications. So for friction measurement, for example, we would often build in our own configuration for friction measurement. And one of our strengths, I think, as a research group, is that we do design and build sensors and develop techniques to measure tribological parameters like leakage, friction, film thickness.
Okay. Excellent. People sort of thank you a lot really for the presentation as well here. Very interesting and well worth getting up for 5 a.m. US time, somebody's mentioning. They are looking at updating a report for the US government on how to reduce energy consumption and help. They may ask you some input to include this as a section in that report. So just a feedback for you, really, more than anything. One other last thing, probably that will be the end of it, really. Interesting talk again. Do you see any potential application in electrified vehicles, given that there is a desire to move to faster motor speeds?
Systems for generating motion in electrified vehicles are often very complex tribologically. So the short answer is yes. And of course, the government at least are driving us towards electrically powered transport from the future. And companies like Jaguar, for example, see their future in electronic transport. Certainly, automotive applications will come forward. I've no doubt about that. I think we will definitely move to increasing numbers of electronic vehicles. Quite interesting, actually, in the UK, we still have a fairly small proportion of electronic vehicles on the road compared to many countries in Europe, and I think we're a little bit behind in that aspect. However, I don't think the tribological challenges will go away. I think we'll also see, in some applications, we'll see increasing use of gas and hydrogen-powered vehicles and power generation, both static and moving power generation. So the landscape for tribology is never static, and it won't remain static. We'll get these hydrogen power system challenges. I think we'll have challenges too in electric transport, which we can address and certainly apply our tribological experience to and address these challenges.
Excellent.
To future demands.
Yeah, thank you very much, Ian. I think you have received some amazing questions here. We covered almost all of them, really. I'd like to thank you so much again for presenting for us, and I want to remind our audience that they should be contacting Professor Ian Sherrington if they are interested in receiving the presentation slides. And also, please follow us on social media or check our website for our future events. I'd like to thank you again for your attention, and we hope you enjoyed the event. I have been Murat Islam, and Emma Pateman helped me with this presentation. And I put down some links for you to check as well. If you don't mind joining us on LinkedIn or anywhere else, that would be really appreciated. So thank you all, and have a great weekend. Thank you.